Okay, thank you very much for the invitation and the opportunity to speak here. So first of all, let us introduce the Anosov flow. So this is Anosov flow is a C1 flow, which admits a continuous invariant DG invariant splitting as such, and N denotes the flow direction, and ES is uniformly contracted by the derivative map, and EU is uniformly expanded. And it is known that for Anosov flow, ES and EU integrate to stable affiliation, unstable affiliation respectively, but usually they don't need to be jointly integrable. Okay, then there were a lot of previous studies about this Anosov flow. For transitive Anosov flows, the following theorem is well known. A transitive Anosov flow is either topologically mixing or it is conjugate to a suspension flow over an Anosov diffeomorphism with constant root function. And we say that G is topologically mixing if for any non-empty open set AB and for all sufficiently large T, this GTA intersect B non-trivially. Okay, then we'll study the mixing property of this Anosov flow. What we are mainly concerned with, we are going to study the equilibrium measure. So what is the equilibrium measure? So given a Helder potential function, a Helder function on M, denoted by F, then it is known that there is a unique measure mu GF which maximizes this quantity called potential, pressure. And so in this case, we say that nu GF is an equilibrium measure for G with potential F. So when F equals to 0, and then this is the entropy maximizing measure, or the Bowen-Margulis measure. So when F equals to this thing, mu GF is called the SRB measure. So it can also be defined in this way. So for this Anosov flow, there's a question saying that there's a result of Bowen and Rel. They show that for C2 Anosov flow, which is topologically mixing, G is mixing respect to equilibrium measure with Helder potential. And then they asked so actually what they proved is more general. They proved in the paper the same thing holds for so-called axiom A flow or hyperbolic flow. And then they asked the question whether or not this speed of mixing can be exponentially fast. I think I defined the right. What do we mean by exponentially mixing? So it means that given two functions, then you know that this is smaller than C minus kappa T. All of these can define on this data, and kappa will usually depend on G and also on theta. Okay. So they ask that whether or not this mixing speed is exponentially fast. Then for axiom A flow, the conjecture was disproved by Ruel. But for Anosov flow, this is not known. What we show is that if you consider three-dimensional Anosov flow and you assume that the regularity is C infinite, then you can have this. You can have exponential mixing with respect to any equilibrium measure with Helder potential. So we mentioned some previous progress on this conjecture. Chernoff, they show that Chernoff he showed that you can have stretched exponentially decay of correlation. So what I wrote on the whiteboard, so this is called a correlation. And what Chernoff showed, I think, is basically about this. So you have this estimate. And then Dolgopiad made the first progress on exponential mixing. So he showed that if you assume that ES and EU are of class C1, then you can show exponential mixing, assuming that the flow is topologically mixing and the equilibrium measure you consider have doubling property. So by doubling property, we mean that so if you have some measure on some space, maybe X, then by doubling property, we say that a mu bxr is less than C mu dx 1/2 of r for all x and r. So what he was the measure what he was considering is this equilibrium measure, but the conditional measure of this equilibrium measure on the unstable manifold. And then Liverani showed that when G preserve a contact form, then you can show exponential mixing with respect to volume. When G preserve a contact form, it is always mixing. And Suji showed that in 3 dimension, and when G preserve a volume form and verify certain C3 open C infinite dense condition, you can show exponential mixing with respect to volume. And there's also a result of Bartley and Wall. So they show that when the this stable foliation is C1 plus epsilon, then they can show this for SRB measure. So there are some other related works. So they show that.
Could I ask about the Dolgopiad result? When the fact that he assumes it's class C1, this is not a generic statement, I guess.
No. Usually it's not C1. In some interesting situations, it is known that this is verified. For instance, for the geodesic flow on negatively curved surface, it is known to this condition is known to hold. And the second condition, equilibrium measure with doubling property, this holds in dimension 3. In general, if you consider a codimensional 1 Anosov flow, it holds if the unstable is of dimension 1. But usually in the general case, I think it's.
Does anybody hear me? I have a question.
Okay.
Peter. Yeah.
We hear you.
Okay. In Dolgopiad, on the geodesic flow in variable negative curvature, so the C1 on the foliations is unstable and stable, but the condition on the metric is that it's what? Smooth. The negatively curved metric, what's the condition? It's negatively curved, but
I think in the paper he wrote C5, but
C5,
he
okay.
said that it can be C2 plus epsilon.
Okay, so it deals with essentially the negatively curved geodesic flow case.
Yes. Okay. Sorry, I don't know how to pronounce this name. Giuliatti. Giulietti, Liravani, and Polycott, they studied so-called dynamical zeta function, and they can show decay under some pinching condition. So what is dynamical zeta function? I wrote it somewhere else. I wrote it, sorry, maybe I wrote further. I wrote it somewhere. Here. Dynamical zeta function is defined like this. You take the product of all the closed orbit, but prime orbit. Then you consider this thing. So they show that this function, so when the flow is C-infinite, they show that this function admits a meromorphic extension to the whole complex plane. And they also show that, already Dolgopiad in his paper showed that under his condition that this function has a single pole on this topological entropy on the rail line, and it has and on this half plane, it has only a single pole at this point, and it's holomorphic on the other part of this half plane. Also, they can also show that Giulietti, Liravani, and Polycott, they can also show this sort of estimate, where this counts the number of, sorry, this T is upstairs. This T is upstairs. This NT counts the number of prime orbits with length smaller than T. Okay. They need to assume that the flow preserve a contact structure, and also they need to assume a little bit pinching condition. Then, if you consider only super polynomial rate of decay, there's a work of Field, Melbourne, and Torok. They show that under generic condition you can have this. And this generic condition is necessary because, as we said, there is a counterexample for axial wave flow by rail. There's a lot of counterexample for axial wave. Then Polycott Sharp, they showed prime orbit theory using Dolgopiad's estimate with this exponential error term. So this is the things that we have just seen. So usually this condition answers Tom's question. So they don't need to be smooth, but they are always holder. And in many cases, in highly dimension, for instance, I know that there are papers that explicitly says that the Holt exponent can be actually small by these people. Right. And our strategy follows closely Dolgopiad's method. So we'll consider a Markov partition. So maybe I say a little bit about what is a Markov partition. So on a manifold, you consider several rectangles formed in this way. So you consider a small local unstable manifold. And then on each point of this local unstable manifold, you consider a piece of local stable manifold. So this is not a smooth object. Like usually this is only a Helder object. You denote this by pi alpha. Then on the manifold you can construct a lot of, but finite many small rectangles like this. And then you consider, if you consider return flow, the first return flow restricted to this objects, then this will be, you denote it by sigma hat, for instance. Then the picture will look like from one piece, then you will map this vertical rectangle to a horizontal rectangle, maybe here. And this part goes here. But you do not allow something like this. This is not allowed. So the existence of such Markov partition is constructed by Bowen and maybe Sinai and maybe Ratner. There were a lot of related work on this. And then the return time function is written as tau. And you can see, you can regard tau as a function on U. What is U? U is the union of all this U alpha. Each U alpha is each U alpha is this. So this line is a U alpha. This is because the stable manifold is invariant under the flow. So the return time function for 2 points here are the same. Okay, then the return map, you can also consider return map as a map on U. Then you denote it by sigma. This map has a Markov property. We have explained this. Consider mu tau as a map as a measure induced by mu GF, and you let mu U be the projection of mu pi to U. And about the foliation, so when the manifold is of dimension 3, you know that this weak stable and weak unstable are C1 plus epsilon foliations. So these are very important for us. This is a result of Hasselblatt's. So as all of the study about this exponential mixing, what is really important is this so-called temporal function. So you consider this this picture. So maybe I try to zoom up the picture. So X is any point on the manifold, and Z is any point on the unstable manifold of U. Unstable manifold. And Y is any point on the stable manifold of X. And then you consider, so then you consider the stable manifolds through X and consider unstable manifolds through Y. They will intersect on a flow line. The distance of this flow line is denoted by this thing written by red letter called psi XYZ. The return, this temporal function, we study this because it's closely related to this return time function. You have such thing. So you consider inverse branch and you consider partial sum of this temporal return time function, and starting from this inverse branch. And the difference about these two between the two takes form of a temporal function. And then we'll consider complex Rel-Perron-Frobenius operator. So this operator takes this form. You consider A being R, and you consider, maybe we say a little bit about this F. So given a capital F, this potential on the whole space, we construct certain, so this is not constructed by us, this is already studied by Ruel. You can associate with that F a function, this little f on U. And the problem for the Anosov flow reduced to the study of this function, this potential, new potential. You consider this operator, EFY, and you apply a plus IB, this is complex number, times the return time. And you act on this U. Okay, this is what I just said. Okay, so main thing we need to study, we need to establish is the so-called Dolgo-Pierce estimate. So it's the following. So you let this be a topological mixing 3D Anosov flow. Actually, we establish this for certain class of Anosov flow, but then the study of other class can be reduced to the case we study just by inverse the flow. So there is a A0, B0, and you consider all the parameter A smaller with modulus smaller than A0 and all the parameter B with modulus bigger than B0. You consider a Hilbert function, and you take n of this size. Then you can show that the L2 norm of this function is smaller than some small inverse power of B times the maximum of these plus this, the maximum of these two things. There are some consequences of this. For instance, exponential mixing is one consequence. There are other consequences like this, but this I have to check, but probably you will work out because in the literatures, all of the, the literature I was looking at. So first of all, the third item is a consequence of the second item. Then for the second item, should be a consequence of Dolgo-Pierce estimate, but this is established in the paper of Polycott and Sharp. But in that paper, they studied C1 function, and this is a C1 function. This is C1, but probably the same thing will work out.
Can I slow you down a little bit?
Mm-hmm.
Okay, so you mentioned a bunch of results at the beginning about results that have been proved before by other people. So what is missing? What is the difference between those results and yours? That's one question. And another question is, you mentioned this gap when you go along unstable, then stable, then unstable, and then you don't close up in the rectangle. I mean, that gap, is that equivalent to exponential mixing? And the third question is, how is that related to the Dolgo-Pierce estimate?
Oh, okay. So in this, for instance, in this work, they need to know these bundles are C1, but in general, it is not C1. It does not need to be C1. This is a difficulty. Another thing is that Dolgo-Pierce proves this for equilibrium measure, but in many other papers, for instance, these three papers, they need to consider certain integration by parts. They need to use argument like integration by part. This only works for smooth measure. So SRB measure, it works. But if you consider entropy maximizing measure, then usually it doesn't work. But if you consider, say, prime orbit theorem, if you consider, say, this thing or this thing, you need to study entropy max imagine measure. And so in that case, usually you don't have the integration by part.
Well, actually, I was asking for something that's on a less formal level, right? Like this property of moving along, strong, stable, strong, unstable, and coming back. Like, yeah, this property here. How exactly is it related to the smoothness of the ES and EU? And are they related? I mean,
yes. So, so for instance, you look at this function. If these bundles are C1, then this is a C1 function. In Docker-Pell's estimate, in Docker-Pell's paper, for instance, it is a C1 function in both Y and Z.
But you still need it to be positive, right? You worry about canceling out.
I mean, not positive, but non-zero.
You're bounded away from zero, no? Do you need it?
Non-zero, yes, bounded away from zero. Eventually, bounded away from zero.
So is that guaranteed by smoothness of the bundles, or where does that come from?
So when both bundles are C1, and when you assume topologically mixing, it is bounded away from zero.
Okay. Okay. So, and how is this related to the this Dogo-Piat? Can you show the estimate that you said you were going to show before? How is this condition related to the estimate, Dogo-Piat estimate? Yeah.
So Dogo-Piat estimate, basically, this thing will. So it's like it's a van der Kuiper's lemma. So in van der Kuiper's lemma, you have a E, I, B, F, X. Then you know basically F increases. Then you have cancellation. Right. So
that lost me.
But isn't the whole point?
Maybe it's going to come up later. But
there's also a complex parameter which is absolutely critical. Van der Kuiper is usually just e to the I phase, real. Yeah.
So this is a real function. If this increases, then you know this is smaller than something. Right?
Yeah, that's state phase. If f is real, you got a parameter a and b. My understanding was that you're complexifying everything there as Dogo-Piat, right? Isn't that important?
Yes.
Then Lai Sang's question, I think, is it not relevant? Van der Kuiper is that, yes. If f is real and highly and increasing, the derivative is large, yeah. But you want exponential decay somewhere.
So because we want to get this sort of cancellation, so knowing that f is differentiable allows us to use, for instance, Van der Kuiper's lemma. Yeah. But if f is only Helder, so in our case, f can be only Helder, and then there's no reason, then there's no general reason why it should be small.
Right.
So you need to use more about.
This bound is just for the the integration by parts. It's not the exponential gain in this part. So I take that back. Yeah.
But how is this related to this this gap that you said? There were two things that you said there, right?
So this gap.
Yeah.
Because you see, this is the difference of two temporal function. Right, and then since we consider have this EIB, this tau.
Okay.
So because you can consider one of this as a fixed. You say this is a fixed, and you move that, right? And you can basically put this in here. You can replace this by that thing, and you add up a constant. And then if that moves, this moves monotonically, and if this is also C1, then you can try to use you can try to extract some cancellation from this information. But if you only know that this is a Helder, then it will be harder to do this.
Is that the fundamental difference? Or is that just one of them?
I think this is the basic difference, the main difference. Because in Dolgopiat's paper, he can also consider the case where F is a Hilder. I mean, he can also avoid using directly the integration by parts. But eventually the cancellation comes from this increase or decrease monotonically with a definite speed. But when it's Hilder, you don't know this definite speed. Should I continue?
Yes, please.
Oh, okay, thank you. So basically, we need to establish this. So this is proved by certain more abstract condition. So maybe for one thing, we can look at that. Okay, maybe I should screen back. We can look at this is the following. So basically, this says that after these many steps, you can see cancellation on scale 1. Scale 1 means the whole macropartition. Then maybe we ask under what scale, at what scale you can see cancellation after one step. So in certain very vague sense. So in Dolgopiat's estimate, the answer is basically B inverse, because you look at this, and if you restrict it to y to an interval of size B inverse, and because also this is a C1 function, then B times tau y restricted to this interval will be basically a fine function. Then a fine function with a slope that is not too big and not too small. And this will give you cancellation. But in our case, it's more difficult to study at what scale you can see similar thing. So this is what we will study. So we will consider a sequence of function. This function will describe the scale we will be working on. So this function, we consider this to be very big. Actually, in our case, this kappa will be bigger than 1, bigger or equal to 1. Then the scale we'll consider is the inverse of this. So let me draw some picture to describe this thing. You have this x. So you take an x, and you take an interval of this x of size this. And this is unstable. Then on the stable, you consider a constant piece, maybe of size 1. And then you consider temporal function like x, maybe y. Let us just for now say y and z are all real numbers. Sorry, this is z. Let's say z and y are all real numbers. And you consider this function. Okay, as this becomes smaller and smaller, the whole thing becomes smaller and smaller, then this will tend to 0, right? It will tend to 0. Okay, we normalize it, then we get this function. We consider this function. So we will take epsilon to be inverse. So you consider this function. We want to find the scale so that this function, so essentially this function lies in the bounded space, is bounded. It's bounded. You want to find a scale so that this function is bounded. So basically, the second thing, this time condition says that the first condition is called stable. Of course, we can choose this at each point so that this is bounded. We just need to choose this to be very, very large compared to epsilon. For instance, we choose this to be epsilon to the power some very large k, then okay, then things will be okay. But this choice is not very useful for us. Also, this time says that basically, since I said for each this x and each y, and you consider this a function as a okay, maybe s, then s can be approximated very well by a Hölder function with a bounded norm. Bounded Hölder norm.
Can you remind me where you're going with this? What are you trying to prove?
Okay, so the things we're trying to prove is the, this is at the very end of the thing. Okay, essentially we are going to prove a statement like this. Sorry, there's a condition to this proposition. I didn't write, but it is under the condition that, okay, first let me mention some other properties. I just said 2 properties, we need several other properties. One thing is that we need to find a set U so that the recurrence is fast. For instance, you choose this to be the whole U, or you choose this to be some passing that you can prove recurrence. The main thing about this scale is the following. It's called the uniform non-integrability condition. We will choose to we'll find this scale so that let me it's better that I write directly here. Okay, remember this is a function of 2 variables, right? We will want to see the following thing happen. For each x, and there exists an interval belongs to this -1 to 1. There's an interval here, say j. The size of the interval is bounded from below. And for each point on this interval, so for each point, so each y on this interval, every y in this interval, you consider this function with this y here being this y. Then you consider this as a function of z. Then the following thing holds for any w in this. There exists also interval. Maybe I write L. So this, maybe this is J1. This is J0. Maybe this is J1. J1 also in -1 to 1. So J1 corresponds to an interval here. So that if you look at this function restrict to y at z inside of this interval, then this function is a kappa away from this omega. So do I make myself clear? So for each x, you can find a small interval on the of definite size on the stable manifold. And for each point inside of this interval, you consider the function as a function of z. Then you consider this function. Then basically this function will not stick to some value. You will take a lot of value. You will not stick to maybe a fixed value. So it will take a lot of value. For any omega, you can find the interval so that on this interval, this function avoid this omega.
Where did this periodicity come from? Or was that just arbitrary choice? This R over Z, why are we dividing by Z in this picture?
What's the
integers?
Integer is basically,
where did the torus come from? Where
it's here. Let me. Recall that epsilon inverse equals to B. And because it is a compact phase, complex phase.
Okay,
so
it's periodic. Okay.
Yes. So this is basically you have some for each phase you can find the interval that avoids this phase.
Yeah. Okay. I get.
So this is the main thing that is responsible for the cancellation. So under these conditions, we'll show the following. So you start from some function, and then so this is, sorry, I made a little mistake here. This is a log B, but it's not really like a log B. Okay, it's a constant times this. It's a constant times this. Okay. So for any of these Holder function, for any AB in this range, you can start from some function. And then so that for each time, and this is also C log B, and each time n in this range, you can show that you iterate this thing. Okay, I didn't explain what is L tilde. You can just think L tilde as a L AB. You just think tilde as LAB here. This in the end, L tilde is something with a smooth coefficient, but this is a smoothing trick due to Doppler to smooth away real part. The real part is very under good control. It's the complex part that is very big. So more convenient to consider the real part as something smooth. And you iterate this operator on this U. So at each step, it will be controlled pointwise by this Hn. And also for each n in this range, you can find a subset omega n, so that if x run into this subset, then this Hn square x will be smaller than one of these. Will be smaller than m. Okay, what is this? So let me write it here. So m is you can just think of this as a 0. No, sorry, A0. So L is a AB. This is how you think about this. So M is the operator that you remove the phase. For instance, if you have U here, and you clearly have u is smaller than mu m applied to the absolute value of u. So I think Professor Lai Yang's question is related to the following. So these subsets, these subsets omega n, you can think of this as a lot of union of intervals of size this. So maybe the good answer is that we construct some scale so that we can find a set on which you can show this estimate, and also this thing is relatively big in the following sense, in the sense that a lot of things run into this sequence of sets with a definite frequency. So if you have this, then you have an exponential decay. Basically, you can think of this as if you have a point. So each time you run into one of these sets, the value will decrease a little bit. Then if you run into this many times, then you will know that the value is small, exponentially small. But if it does not run into it very often, such point will be rare. So this is the basic thing that we use this scale. The proof of this is basically consider some random process and define as follow. You can show estimate like this. Then only need to consider x so that you run into this set very fast. But each time you run into this gm plus n will be a bit smaller than gmx. So if you run into this fast, it will be very small. So in the end, you can conclude by 1. So this is where you know the L2 norm of this is small. So okay, maybe this is about how we show each property. So in the end, the first property is because you have this sigma is an expanding map. So the Helder norm will be the Helder semi-norm will be good compared to the previous one. But there was some the problem came from the complex phase. So if you just consider m will make this m. Without complex phase, it will make the Helder norm smaller and smaller. But consider the complex phase. The non-smoothness comes from the temporal function because you have b times temporal function. But that is also controlled because we have this m condition of the scale we constructed. So in the end, these two things altogether give you this. And this is a technical condition, and this non-uniform integrability condition allows us to find this set. Or you can think of in the picture I drew. So each time you find for each omega, you can find an interval here. This interval is have definite size. Okay, I didn't write, but this interval is also bigger than kappa. The size of the interval, both intervals are bigger than kappa. So in the end, this omega n is a union of interval that looks like this. That is chosen by this uniform, non-uniform integrability condition. The union of interval like this. Then the last thing is this recurrence, because the main thing is that this set will change at each step. Because at j step, you want it to run into sigma omega j. It will change from time to time, but this is also not a problem because all of these omega j will be in certain sense dense and thick in omega. So you can compare this with you can compare the return map to omega. Basically, you can do some coupling so that to show the recurrence property to this sequence from the recurrence property to omega. Main thing is how to construct these scales. Okay, so it is a bit technical. We divided this into several cases. In one case, you assume that neither this EU nor this ES is smooth. Also, you can assume in addition that the average divergence is non-positive. If it is a positive, then we reverse the flow so that is non-positive. Then there are two other cases. This classification is tautological because any flow must be one of these class. So without the loss of generality, you can assume that in the other cases, EU is a C1 plus epsilon, C1 plus tau. So basic is that we can, if you start from Anosov flow in class IF or 1F or 2, and assume that they are not jointly integrable, you can construct these scale functions with all of these properties. And you can also assume that this non-uniform integrability holds at these scales. And the proposition is that if this thing, you can find such thing, you can show Dolgopil tensor.
So can I interrupt by asking you, where does the property of being an equilibrium measure come in?
Doubling property.
But so any measure with the doubling property?
And also, so the way we use equilibrium measure is the same way Dolgopil use equilibrium measure. There's not any difference there. So basically,
can you remind me?
So basically, he can transfer. So if this equilibrium measure, you can transfer the study of this thing, this flow on the manifold to this study of this. You see, this is a mu u. Mu u is this measure projected to this unstable.
But it doesn't have to. I mean, what does this have to do with these little intervals that you are constructing and the fast recurrence?
So in that part, we don't.
That has to do with mixing and not the measure, right?
Yes. That we use, basically we use mixing. We don't use any additional property, except that we use it is a doubling measure.
Thank you.
We consider these two cases, but I will not have enough time because it's technical. Let's just say difficult case is basically class 1. And then is to show that, okay, so yes, the difficult case is class 1. For instance, if you don't care about the other equilibrium measure, if you just care about SLB measure, then the proof for class 2 and 3 is already done by Bartley and Wu, and under even more general condition. In that case, they don't need to assume anything about the dimension. In our case, we use the same abstract scheme, but we construct this. Okay, so in the end, basic thing is that we need to give a good approximation to the temporal function. So that is the main technical part. To give approximation to this is a bit technical. So basically, first of all, you know that on each point on the stable manifold and also unstable manifold, you can, in some sense, parameterize things canonically. There are so-called non-stationary normal charts for this stable manifold and also unstable manifold. And then we will construct something we call normal coordinate system. So this is a flow chart. So this says that this is a flow chart, and also this parameterized in the unstable normal coordinate chart. And this is the stable coordinate only at 0. Okay. But then this is the main thing. It's the transformation between charts. So we said that this transformation, without any additional thing, you can always assume that it takes this form, because this is simply because it is a flow chart. Then these are polynomials of degree k. These are polynomials of degree k. So this, and also these are both constant functions. So under this coordinate system, we can, in some sense, straighten this center unstable foliation. Only near this plane, only near the y equals to 0x. So I think I drew a picture here. So this is the stable, this is the unstable, and all the vertical lines are the flow line. Okay, so maybe I start from this picture. There are two, so given this chart, there are two plane fields that is worth mentioning. One is the basically trivial plane field, t equal to 0. So I only consider plane fields on the zx. So there's a trivial plane field. This is a smooth plane field because the chart is smooth. Everything is very smooth. There's another plane field defined by the dynamic. It's a EU plus ES. So on each point, you consider EU plus ES, and it's of dimension 2 is a plane field. So you see, this thing is not smooth, but it is invariant under the flow. This thing is smooth, but it's not invariant on the flow. It will turn under the, from chart to chart, it will twist. But our condition, our choice of the chart will tell you that angle from this to the next one, you only consider in plane field 2. The angle of the twisting is a polynomial function. And the degree is bounded everywhere. So we will consider the angle between these two plane fields and consider tangent of this. So we will basically approximate this temporal function by so this angle, this function, we call it template, is a building block of the approximation. We can approximate temporal function by function with a simple forms. So you have a Hilder part, you have another Hilder part, but the other part is a polynomial function. So okay, so this is the main thing. Also, you may think that this chart is constructed in a very artificial way, because maybe you construct it differently, you get another chart. But all these charts will differ from a polynomial phase, so from some polynomial. If you construct another chart and you define this, and that is only, you only need to modify this thing by adding another polynomial. So up to a polynomial is unique. So that is one change. Then, so in the end, the observation is that because to show exponential mixing, we need to get some, need to know that this temporal function, it cannot be all zero. It cannot, if it is not all zero, it cannot have exponential mixing, or even in this case, not even mixing. Also, it cannot be very strange. Like you cannot have a very long piece so that the temporal function at zero, like very close to zero, and for the other part very big. So this approximation will allow us to say that, so this temporal function shares some feature with a polynomial. If you know the temporal function is big in the interval of size 1, then you know that this temporal function is not extremely small on any interval of size, say, 1/2. So this will give us a lot of information. Then also you can use something called the Journet's lemma to show that as long as this, as long as you are in class 1, then all of these temporal function will be bounded away from polynomials. So at any point, the temporal function will be, by polynomial, I mean polynomial of degree k. Of course, you can use a very large degree polynomial. We don't consider that. We only consider polynomial of degree k. So if you are in class 1, then at each point, the temporal function minus any polynomial will be of C1 norm, a C0 norm bigger than, say, kappa, something like this. So this is the basic main mechanism for our cancellation. So this is the function. You can, so this is the renormalized temporal function. You can approximate this by something formed by templates plus something. For fixed y, this is also a polynomial, but the dependence on y is less clear. But in some case, we don't, for some general, in a lot of places, we only need to know that it's a polynomial in Z. But in some places, we need to know that it is also a polynomial in Y, or it has a good dependence on Y. So this approximation proposition tells you that if you choose this scale in a good way, satisfy this condition, then this will be controlled, and also the degree, the precision of the approximation is also good. And also this R is sort of bounded. illustration of the idea is the following. Basically, we want to study the distance between these 2 points. They are on the same flow line. You consider this thing to be very small. But then you can know the coordinate of this P0 very well by approximation, by linear approximation of the template. But then in that case, you cannot understand this very well because this line is a bit long, and also this line is determined by the future. So in some sense, this is hard to describe. But image of this point is easy to describe. If you iterate this picture several times so that these points become very close to this x, to this horizontal x, when this is very small, you can do linear approximation to describe this point very well. But in that case, you cannot describe these points anymore. But it's okay. So what is in between is a coordinate of this, and the coordinate of this, and a coordinate change from this chart to this chart. There's a coordinate change. You have to consider how coordinate changes. In the end, you can understand this because these coordinates are chosen in a very, very good way. Though you don't know how precisely it change, but you can know that the change is a polynomial of degree k. This is the information we know. So we can know that the change of coordinates is a polynomial of degree k. So then there are certain. Okay, so this picture maybe we don't explain too much. But then you choose this scale in the following way. You consider n to be the first number so that both of these are small. So this condition is to ensure that this picture, this is smaller than epsilon, and this is also smaller than epsilon. Then you also ask that basically this thing. Basically, you want to know you choose this so that if you put epsilon inverse here, if you put epsilon inverse here, the things will be bounded because like both of the sides you have a epsilon. So this is our purpose. As I said, we want to choose a scale so that this rescaled temporal function is bounded. So after we make such choice, we verify some property of this temporal function. Property we verify is these properties. We verify all of these properties. And then we use this abstract scheme to prove exponential decay. So that is basic our talk.
Thank you. So I guess there are questions.
Firstly, there was a question on the chat.
Oh yes, that's true.
Whether there's a manuscript available, perhaps you can make clear as to where people can get a copy, or whether it's ready, or what you.
Like we are finalizing this. Like probably we finish this in 2 months, maybe 1 month and a half.
And if somebody were to ask you for a copy, would you give it to them? Well, they can do it, I guess. You can. I
think I already gave some other people, but there are some small mistakes inside of the note I wrote, but they're only very minor mistake. But okay, there are a lot of them. But we are trying. We are we are basically getting very close.
Okay, it's just somebody watching. I would want to see more detail. Obviously, this is technically very, very complicated, and so the slides will be available, right?
Yes, yes.
I have a funny question to you. Suppose I give you an Anosov flow as in your setup and you have exponential mixing. Is your proof effective? I don't want you to give me epsilon in terms of any data, but in principle, if I put a gun to your head and I said, could you compute what epsilon is in terms of the given data?
Epsilon, you mean, by epsilon, you mean
exponential, the mixing rate.
Okay, so the rate is as follow.
In other words, can you actually give an estimate in terms of all the norms of everything around?
Let me think a bit.
I'm not even asking you in practice, I'm even asking you in principle. Because you're doing such a... Of course, if you were to give it in closed form, that would be the best, right? There's a number epsilon, depends on all these norms and the minimum of this, and this.
I think if you can calculate everything at every point, then it is.
Zhiyuan, are you sure? Because if I remember correctly, the method of Dolgo-Piat depends on trying to estimate the B naught from where you start getting cancellation. And that argument ultimately comes from a compactness thing. So there, something is non-effective, if I remember correctly.
Or at least you have to estimate usually then some modulus of continuity. I just want to distinguish between putting a number and in principle, yeah.
So it's like this. When B is very, very big, then you can show this. You can show this a zone with no pole. But inside of this bounded zone, there could be some resonance, and then our method cannot tell you where the resonance is. But you know that there are only finite many resonances, and also there are no resonance on the X, because mixing, there are no resonance on the imaginary X. So
such an argument could be ineffective in the sense that you don't know the distance to the axis, but just that it's not on the axis. Yeah. Well,
I think if you only consider this essential spectrum, so there is a essential spectrum and a spectrum. If you consider essential spectrum and the essential spectrum gap, I think the essential spectrum gap is okay. It's expected. If you can calculate everything at every point, but then away from this, outside of this essential spectrum, there are a lot of other resonance, and for that, I don't know. It's not related with our method. Is that what Carlos Mateus said?
Yeah, exactly.
Oh, okay. So yeah, so it depends on some function. If you outside of finitely many functions, outside of a finite dimensional set of functions, then the decay of function will be exponential of the essential spectral norm, essential spectral gap, and that gap is explicit. Does that answer your question?
Yes, I think so. Yeah.
So I have another question about your result is three-dimensional, right? Because you're using very strongly the fact that the EU is one-dimensional, correct?
Yes.
So what did Liverani and company, or maybe just Liverani, do? Didn't they have a result for high dimensional contact flows. Why is it that they were able to get exponential?
So in contact flow, so I think even in contact flow, you don't really know that if a stable and unstable affiliation are smooth. But the following thing is smooth. Let me show you. So this thing is smooth.
The EUs plus ES is nice, right?
Yes, EU plus ES is
it's
the
smooth,
kernel.
right?
Yes, is the kernel of the contact form.
Right.
So this is a smoothing.
So you use that instead of what you.
No, they use that. So
okay.
In that case, this is smooth.
Okay.
So if you preserve a contact structure, this is infinite smooth. You can just choose this plane field to be this.
Right. And with that, then you don't need these other.
Yeah, and then this is zero. This is zero everywhere.
Mm-hmm.
Everything is just.
Okay.
Mm-hmm.
But you don't have this doubling property or any of those things, then, or do you?
Like we have this doubling.
No, but in the high dimensional case, you don't.
In higher dimensional case, they prove this only for measure for volume.
Only for SRB, right?
Volume has a doubling.
Yeah. Okay.
In your case, besides the SRB and the measure with maximal entropy, what other measures, invariant measures, does it apply to? I mean, are there other interesting measures? Probably, but I don't know.
Actually, I don't know about this.
Okay.
Maybe I don't know about this. Like usually.
The one of maximal entropy is my most dear one anyway. So capturing to me the most interesting.
Okay. If there are no further questions, let us thank our speaker again. Thank you.